Good morning. This is David Harlan, Adam Carr, and Samuel Valdez, and today we will be discussing about our process control project. Today we will be talking about controlling pH in bioreactors. Some topics that we will be covering are the theory or the need behind growing phages and bacteria and their relationship to bees, model fitting results that we got after fitting an FOPDT model to our system, some stability analysis discussion, and about future work. Now, we need to start talking about what's the purpose behind all of this? Well, bees are essential for agriculture and the world food supply, but lately their populations have been in decline. So we work in connection with a small biotechnology company which grows bacteria in these bioreactors, this bacteria being harmful to bees, and they later develop the phages that attack these bacteria so we can later treat the bees. Some equipment that we use, our bioreactor is the BioFlow 320. We control the pH and the dissolved oxygen levels. Our actuators include the on and off switches for the acid and base pumps. How we went about this was first prototyping. We developed a primordial physics-based model behind our bioreactor controls. Later, we collected data on pH and the concentration levels. Then we developed the FOPDT model by obtaining and tuning the fitting parameters that accurately model our behavior. And later we refined our model by using some gain scheduling and open loop control so that we can accurately reflect our set points.
So the first step in building the controller is to find a way to linearize pH through concentration. That's done with these equations right here at the bottom. You can see the graph on the left is a pH titration curve, and the graph on the right is the linearized concentration curve. So we developed a PI controller, and our initial tuning parameters were found with the IMC tuning correlations from our physics-based model. And then we just began to perform doublet and step tests on the controller and tried to start tuning the parameters. One thing we noticed is that around the pH of 7 and kind of in that range right there, we needed to implement some sort of gain scheduling function because the gain value was off. And so that's what we did in our controller. Is right here we have a function that if the pH is set between 5.1 to 6.6, so an acidic set point, then it'll just change the Kc value. And we do the same for the base. So if the base is set between 7.3 and 9.5, then any of those in that range, then it'll change the Kc value. And where things got interesting is right around that equivalence point, right at pH of 7. The slope actually goes to infinity, and so that made it really tricky to control pH. And so what we did to fix that is we actually changed the output. So we let the controller calculate how much it should add, and then we set up a function that just that modifies that output. And you can see that right here, the code. So after all this, we found that we had a really robust model that could reach pH set points in a wide range. This is a simple test right here showing the edge cases. So very high pH, low pH, and then a pH at 7. You can see the controller is really good in reaching those set points.
And so as we discussed, that the pH range was quite robust. Here's just our physics-based FOPDT and graphical methods to get our initial tuning parameters. And the pH range was actually between 3.8 and 10.8, which was a wider range than the BioFlow 320 reactor, which was between about 5 and 10. And this was due in large part to the gain scheduling functions which we implemented, and also the output manipulation around the equivalence point that we did to have it not overshoot the pH when it got close to that slope of infinity. Now the PI controller worked really well. However, we determined that since pH is really an integrating system, that we could, in theory, implement just a P-only controller, and that should be sufficient. So as a future direction, we would like to implement a P-only controller in a system like the BioFlow 320 to see if it is sufficient to control the pH and maintain the set point.